Let's take a look now at Momentum Homework 1, numbers 5, 6, and 7. Number 5 says, rock climbers use ropes to keep them from falling to their deaths. These ropes are stretchy, not like bungee cords, but compared to steel cables, they're stretchy. Let's consider a 50-kilogram climber who falls 2 meters. So let's calculate the speed she is moving just before she is brought to a stop. So this is actually a problem that we could do in a bunch of different ways. The easiest way is to import an equation that we used earlier in the school year. You could do this with energy, or you could do it with the kinematic equations. Either way, you end up with this idea that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration due to gravity times, in this case, the delta y, which is her vertical displacement. So we look at these. It says calculate the speed she is moving. So we're actually going to calculate the speed here. Because it's v squared, we lose the direction component of the velocity, but that's all right. So v squared, that's what we're solving for. She falls from rest, so 0 squared plus 2 times negative 10 is the acceleration, and she fell 2 meters, so negative 2. So v squared is equal to 2 times negative 10 is negative 20 times negative 2 is 40. So v squared is equal to, Lord, what is root 40? Oof. Okay, 6.3. 6.3 meters per second. Now, the idea here is that we know, typo, you gotta square both sides. We know that this could actually be plus or minus, so we don't know the extent to which she's moving up or moving down. In our context, she's actually moving down. The velocity would be negative 6.3, but because we're just looking for the speed, we're gonna go with 6.3. This is A. B says, calculate the force on the climber if she is stopped by a stretchy rope in 0.05 seconds. Okay, so this looks to me to be one of these momentum questions. So let's look at B. So calculate the force on the climber. So we know that the force times the time that the force is applied is equal to the mass times the change in the velocity. So do we have all these pieces to our puzzle? That's a great question. We're solving for the force. We know the time it's given. We know the mass of the climber, and we're going to get the change in velocity from the part up above. So the force times the time, 0.05 seconds, is equal to the mass of the climber, which was 50 kilograms. Now her change in velocity, she's falling, she picks up speed, so she's moving at a fast 6.3 meters per second, and then the rope brings her to a stop. So the final velocity is 0. The initial velocity was 6.3 meters per second. Now, the thing is, though, that this is the change in velocity, so she was moving in the down direction. So it's actually minus a negative 6.3. We're going to get the same answer because 0 plus 6.3 or 0 minus 6.3 is going to give us the same numerical answer, but the direction is going to be different. So to solve for the force, put it into your trusty calculadora. So it turns out this is 6,300 newtons. So that seems like a lot, okay? The problem says multiply by 2.2 to get it in pounds. That's like 13,860 pounds. Now, that's interesting because 13,000 pounds, that seems like a lot, and it is, okay? Oh my gosh. I totally type, I'm like, that's too many pounds. Sorry. There we go. 1,386 pounds. Now, that's 1,386 pounds and that's applied over this 0.05 seconds. So it's not all at once, it's applied over a longer period of time. The next part says, well, calculate the force on the climber if she was brought to a stop in 0.005 seconds. All right, so let's do C up here, okay? So we're going to use the same idea here. Force times the time the force is applied is equal to the mass times the change in the velocity. So we're going to calculate the force. This time it's 0.0005 is equal to the mass, which is 50. Again, same change in velocity. 0 minus a negative 6.3. This time the force turns out to be 630,000 newtons. So if you're brought to a stop in 100th of the time, the force on you is 100 times bigger. This would be that'd be 138,000 pounds, and that would be too much. That would rip somebody right in half. So the question is, looking at these two numbers, why do the climbers prefer the stretchy ropes? And the answer is, the stretchy ropes increase the stopping time which decreases the stopping force. All right, let's move on to 6. Six says, a carabiner is a metal oval-shaped device used to connect rock climbers to ropes. A certain carabiner can supply a maximum force of 2,200 kilonewtons, or 22,000 newtons. A 50-kilogram rock climber falls off a rock face and the rope brings him to a stop in 0.05 seconds. So this is like the last one. Determine the maximum impulse supplied by the carabiner. What a great question. So in this case, when we look at this one, so we have, I forgot the last one, let's list what we know. So the maximum force is 22,000 newtons. The mass of the rock climber is again 50 kilograms. And the time that the force is applied is 0.05 seconds. So we want to calculate the impulse. So A says find the impulse. Well, the impulse, change in momentum, in this case, it's equal to the force times the time the force is applied. So if I go to calculate that, I know the force, the maximum force is 22,000 newtons. The time is 0.05 seconds. Multiply those two bad boys together. So the change in momentum, the impulse applied is 1,100, and in this case it's Newton seconds because I applied a force times the time. All right, so that's A. B says determine the maximum change in the speed. Now, it could be change in velocity, but we understand what we're talking about here. So B says basically find the delta V, find the change in the velocity. Well, we know that the change in momentum is also equal to the mass times the change in velocity. And now we can just plug and chug this. If I know that this is 1,100, the mass is 50, and we get the V final minus V initial. Actually, this time it asks for the change, so we're just going to calculate that out directly. So the change in velocity is equal to 22 meters per second. And then what is the distance they fall? Again, this is the kind of thing where basically what we're doing is we're just choosing an equation, we're plugging and chugging. You don't really need a conceptual framework to do this, which is why it's like my least favorite kind of problem, but we're going to do it anyway. So now it says if your change in velocity is 22 meters per second, what is the maximum distance that the climber could fall? So basically, if we have our change in velocity is equal to 22 meters per second, I know that that's the V final minus the V initial. Now, in this case, because the climber is falling and then coming to a stop, the V initial is how fast they were moving before the rope caught them, and the V final is 0. So if that is the case, if 22 is equal to 0 minus VI, I know that the initial velocity is equal to 22. So go back to that equation we used on the last one, V squared is equal to V initial squared plus 2G delta Y. The final velocity is oh, that's not right. This is for the falling. So in the falling case, this is actually backward. So this is for the falling. When you start to fall, the final velocity is, when you start to fall, the final velocity is going to be the 22, because when you start to fall, this is 0. So it's the final velocity that is 22. So when you go to plug this in, this is the delta y is how far you fell. So your final velocity is 22, you fell from rest, so that's 0 plus 2 times negative 10 times delta y. So let's see if we can calculate that real fast. So I have a delta y equal to negative 24.2 meters, which means they can fall a distance of 24.2 meters, which is a really long way. I mean, no rock climber would actually fall that far. You're actually only falling a couple meters at a time because you're always clipping yourself in as you go. So that's why they make these carabiners so really, really, really strong, just in case, you know, either you fell from higher or one of your holds broke. This is way farther than anyone would fall, and so that's why they're just trying to be safe with these super strong carabiners. All right, let's do one last one. I didn't realize the light was off. Hopefully you could see it, not a problem. Let's look at the last one. So a golf ball weighs 0.5 newtons, is dropped from a height of 100 or 1.25 meters. Assume that the golf ball hits the ground and loses no energy, so that it rises back to its initial height. I know it doesn't really happen, but let's just figure it out anyway. Determine the time required for the ball to reach the floor and the speed of the ball just before it hits. All right, no problem. Let's go ahead and do that. So let's write down some stuff about the golf ball. First of all, if you diagram it up here, it says the golf ball is dropped from a height of 1.25 meters. So if you want to know how far it fell, initial velocity, final velocity, acceleration and time. How far it fell is negative 1.25 meters. You dropped it, so the initial velocity is 0 meters per second. You don't know the final velocity. You know the acceleration is our g value, which is negative 10, and the time is what you're one of the two things you're solving for. So this problem can be done pretty simply with some skills that we have from before. we can use this equation. Delta y is equal to 1/2 gt squared plus v0 t. We can plug a jug. Negative 1.25 is equal to half of g is negative 5 t squared, plus you dropped it, so this is 0t. So I take 1.25 divided by 5, which is 0.25, and then take the square root, and t is equal to 0.5 seconds. So that's the time it took. So that time is 0.5 seconds. And now it says, well, what is the speed? Well, you can do this one of two ways. One thing you know is that the velocity is equal to the acceleration times time plus the initial velocity. So you could say my velocity is equal to my acceleration, which is negative 10, times 0.5 plus 0. And we see that v is equal to 5 meters per second. Velocity is negative. Or you could use your brain. We know the g value is negative 10 meters per second per second. That means that for every 1 second, the velocity changes by negative 10. But it's not a full second, it's only a half second. So if in 1 second it can change by negative 10, in a half a second, the new velocity is negative 5 meters per second. All right, so that is A. The time is 0.5 seconds, and the velocity is negative 5. That's A. What about B? Well, B asks, what will the momentum of the golf ball be immediately before it strikes the ground? So right here, right before it hits the ground, we know it's moving with this velocity. And so if I want to calculate the momentum is equal to the mass times the velocity. The mass of the golf ball, oh, see, that's sneaky here, because it says that the golf ball weighs 0.5 newtons. So that's actually not the mass. Let's see how we can figure out the mass on this. Well, we know that the weight of an object is equal to the mass times our baby g value. That's our gravitational field strength. So if it was a 1 kilogram mass, it would weigh 10 newtons. A 2 kilogram mass would weigh 20 newtons. Well, this is it weighs 0.5 newtons, and so the mass in this is 10. So the mass must be 0.05 kilograms. See how sneaky that was? And the velocity is negative 5. And so the momentum is 0.25 kilograms meters per second. Now don't forget the fact that it's negative here. The fact that it's negative means that the velocity is in the down direction and the momentum is also in the down direction. Momentum, like velocity, has both a magnitude, a size, and a direction. Don't forget that part. It says, what will the momentum of the golf ball be immediately after it strikes the ground? So now it is hit and now it's back on its way up. And it wants to know what the momentum is right here. Well, we're going to use symmetry as our principle here. We know P is still equal to mv. We know the mass of the golf ball hasn't changed, 0.05. And if it doesn't lose any energy, if it's moving at 5 meters per second as it strikes, it's probably moving at 5 meters per second in the other direction after it comes up. So, but it's not negative 5 now. This time it's positive 5. And so the new momentum is plus 0.25 kilograms meters per second. So this is interesting to me because it went from negative 0.25 to positive 0.25. So there's a large change in momentum here. All right. But we're going to have to see if we can't figure it out. So it says, D says, what is the change in momentum of the ball from right before to right after? No problem. Let's do that. Let me do D up here. So the change in momentum, you could do it by calculating the mass times the change in velocity, or if you're sneaky, you can realize that this change in momentum has to be equal to the final momentum minus the initial momentum. And if we do it that way, the final momentum is 0.25, and then the initial momentum was negative 0.25. And so the change in momentum here, well, it's minus a negative, so we're adding, is 0.5 kilograms meters per second. Again, the change in direction allows you to add the negative. And the last part says, let's suppose that the golf ball was in contact with the floor for 4 times 10 to the negative 3 seconds. No problem, we can do that. What was the force on the ball while it was in contact with the floor? So in this case, if we were to draw a force diagram for the ball, so this is the floor, it's hitting the floor, and here's the representation of the ball. We know that the earth is pulling it down, but the floor is pushing it up with a much bigger force. So we're going to calculate the net unbalanced force in this one. We know it's going to be the difference between them. So E, we know that the force times the time the force is applied is equal to the change in the momentum. So I'm looking for the force. I know the time is 4 times 10 to the negative 3. And that's equal to the change in momentum, which is 0.5. Let me get out my handy dandy calculadora. So we have 0.5 divided by 4. And I end up with 125 newtons. So in this case, this is the net force. We know the earth is pulling it down with this 0.5, so then the force by the floor would be 124.5. So the floor would be 120, oh no, it's got to be more, 125.5 newtons, and the ground is 0.5 newtons, because this is the net unbalanced force. And that's all for momentum homework 1.